So without further ado, I'll invite Ron up here to kick us off. Thanks.
Thank you and good morning. I'm the guy that in 2006 met somebody called Avinash Kaushik at a restaurant, and we talked about controlled experiments, and he said we use the term hypo. Well, hypo at Microsoft means high potential. And I went back to Microsoft and thought. We decided to come up with the word hippo and use it, and that's why there's a lot of hippos out there that I gave you out today. We made thousands of these at Microsoft to be able to try and change the culture as we built this experimentation platform. What I want to talk to you today is about the challenges that we face. These are all real. We care a lot about them. We think a lot about them. There's a lot of information in the slides. And if any of you want to talk to us or have ideas about them, would love to hear them afterwards. So with that, let me get started. This is the challenging part. There's a lot of animation through the slides, so if you can get this to work, it will really help me. Okay, so the first challenge that we have is sessions per user. When you think about optimizing a search engine like Bing, which is one of the areas that we do a lot of experiments with, or even other search engines, the main goal is to get what's called query share. What is the share of overall queries that are being run, say in the US? What is the share that you get on your search engine? And the second thing that you optimize is revenue. And so the first observation I want to make is why this is so challenging and why this cannot be the thing you're optimizing for. Right? Even though it's an organization you're trying to optimize for query share and revenue, it is the wrong thing to optimize in controlled experiments, and here's why. So there's a ranking bug in an experiment that resulted in really poor results. Terrible, terrible results were showing up. So what does this do? It causes users to refine their queries, right? They type something simple, we don't get it, the results look poor, they add a couple of words to it, so they issue another query. And the other thing that happens is that the ads, which are not impacted by this bug, suddenly appear better. Right? Because if you degrade the algorithmic results, well, relatively speaking, the ads are going to look a lot better. And so what happened? So distinct queries went up 10%, revenue went up 30%. So that if you ran this as an optimization criteria, your solution should be to kill the relevance team. Okay, so clearly this is wrong. And so the question is, we talk about this concept called the OEC. What is the overall evaluation criteria that you should use for a search engine? And so I'll just make this simple observation. If you care about the queries per month, right, or per period, we can decompose it into queries per sessions times sessions per users times users per month. This is just simple math, right? These just cancel out, and you end up with queries per month, right? So there's nothing complicated here. I'll also mention that if you like task instead of session, that may be more accurate. It's slightly harder to implement. So the key observation is we want users to find the results quickly. Right? They issue a query, boom, we give them the best result, they get out, they're done with their task. And that means that we want to minimize queries per session. Okay, so if we want to optimize for queries per month, we actually want to minimize this. This is where the bug occurs, but we still want to optimize or increase sessions per user. Okay, so that's the key observation that we're making here. And this seems like a really, really good thing to optimize. Okay? And so let's assume that we're trying to optimize for session per user. And by the way, this seems like a really good idea for many sites. You're a site, you want people to come back more, repeat usage. So what's the problem? If you use the t-statistics, and I'm just going to put the few things out there, normally you look at a confidence interval, and because you admit more users into the experiment as the experiment runs, typically that square root of n in the t-statistics makes it go down. The confidence interval shrinks as the square root of n in the denominator goes up. It is not true for sessions per user. Okay, so we found this true for many count metrics. This is the confidence interval over 30 days, and you can see that actually goes up in the beginning and just stays stable. So this is something that worries us a lot. We don't have a good solution for it, and I'd love people. There's one paper that I found that somebody showed that if you look at some Saron Rosette showed that if you look at some negative binomial distributions, this could explain that. Very surprising. Why is this important? This is our North Star. Like, this is the thing that we're trying to optimize all the time. And we know that if you degrade the site, people stop coming. We see that really, really quickly. So if there's a bug, we can find it pretty quickly with sessions per user. The problem is when you try to improve sessions per user, the movements are really rare. Most of our ideas don't cause users to come more. So we created this process called certification that allows us to double check the results of an experiment, replicate it, and see that this is true. Now we run something like 10,000 experiments in a given year. There's about 1,000 to 2,000, so about 10 to 20% of our experiments that we consider to be successful, meaning they end up being at the website. We ship them. There is a handful of them, about 2 or 3 per year, that move sessions per user. Okay, very, very low success rate on that one. So the problem is we just, do we not have enough sensitivity? Are we just stupid with ideas? So can we improve the sensitivity? Okay, we've had one really interesting breakthrough for us, which some of the statisticians will recognize. We use the pre-experiment data to help us reduce some of the variance in the metric, and that has helped us a lot. But could we come up with a different metric that is more sensitive? Is it possible that this metric just can't be moved much? Well, we sort of rule that out because we know that Google has a much higher sessions per user rate than we do at Bing. So very, very interesting challenge for us. The second one, and I'm just going to go through a few of these problems to share with you, is just the whole p-values metaphor, right? Everybody knows about the null hypothesis statistical testing. It's a standard. I'll also just throw in a few there. A lot of people misinterpret it. Hopefully this audience knows that some of these things are, some of these statements are incorrect and why. But the problem is basically we're given the probability that x, the random variable that we're looking for, is greater or equal than the observed, given the assumption, given that the null hypothesis. Right? But that's not what we want, right? What we want is really the opposite. The probability the hypothesis is true given the observed value. And so there has to be some sort of a Bayesian statistic inversion here. This is especially interesting for sessions per user, which I mentioned in the prior problem, because remember, this thing moves at a very, very low rate, right? 2, 3 results per year for us, right? So if you just think of the normal statistics that we do, which is 5%, you're going to get tons of false positives. Right? 5% of the time, somebody will celebrate that they've just moved sessions per user due to chance. And so our process is to certify that, run it again, replicate it, look for very low p-values, but it's pretty hard. And so we are trying to do some Bayesian mechanisms to take that prior into account. Not obvious how we do this. It's not obvious. People say, well, using a low prior, for me, I'm more successful than other teams. What can we do here? Okay, third problem. Duration of the experiment and what are called novelty effects, right? How long should we run an experiment? We typically run experiments for 1 to 2 weeks. We've noticed that for most of the cases, things stabilize after several days. And we run our experiments, by the way, typically with a minimum of 1 million users. This is sort of the standard thing. You start really small, you look at it for a few hours, looks good. You ramp it up to something like 10 or 20% of the population, and that gives you several millions of users in the experiment. If you're running something narrow, what's called a triggered experiment, where you're just looking for a small subset of the population, we'll run it at higher percentages. But we're talking about relatively large numbers, millions of users. They stabilize really quick for most of the stuff. But we have this question about what we call novelty or primacy effects, right? There are some things where users take time to adjust. Right? Maybe it's a feature that you have to try it a few times before it becomes useful. Maybe it's a feature that's hard to discover. So there is a question about whether we should run some experiments longer, or can we alert that something looks like it's improving over time? It's very easy, by the way, to get into fitting problems where people think their feature is improving, and there's a paper that we wrote on that a couple of years ago called Puzzling Results. But when we run experiments for 3 months, and we've done that on some experiments that we think have this novelty effect, very rarely do we see this. There's actually a very interesting paper at KDD that was basically talked about a couple of months ago in Sydney when we were there, and they show that when you change the number of ads on the page, you initially, of course, make more money, but over time, things decrease. So that's a really good example of why you want to run an experiment longer. We have a different interpretation for what happens, but I think that's not the focus of this. Okay. Next challenge is our OEC, the overall evaluation criterion. So we look for a single, possibly weighted metric that determines whether to ship a feature, right? Remember, we're trying to get an org to align behind what is good for the user. Now we know that there's some features that are not, we're looking for this query share and revenue, but we know we can't measure that directly, so we have to go with other things. So the big example that I give first is a good one, but what are the properties of good OECs, right? What is measurable in the short term that is predictive of the long term is the crux of the problem, right? We want to really optimize lifetime value in most of the scenarios that we work with, right? Most of the sites that we work at Microsoft, we try to come up with some measure of lifetime value of the customer. Think of a site like support.microsoft.com. It's a support site. What should it optimize for, right? I was in this meeting, which was really interesting because several people came into the room and they said, look, Ronnie, we studied your papers. We know what the OEC is. It's time on site. And then I said, is more better or more worse? And then half the room split. Right, so it's not obvious what you should be optimizing for. If we now start running experiments on Office, right, Word, Excel, what is really the OEC for these products? Right, so these are things that we think about. And I want to give you a fun example, which very, very debatable. At Microsoft, we've discussed this for basically the last year, which is how do we value standards or design? Okay, so here's the really cool example. On the left, you see the search page with underlines. On the right, you see the search page without underlines. Most people, by the way, if you ask them, when did Google remove underlines? They can't recall. When did Bing remove underlines? They can't recall. So many sites have used the sort of the underline standard or the non-underline standard. But the theme is to move to no underlines these days. The design, the minimal design, the modern design, they're all call for that. There's one big problem with that. All the metrics tell us that removing underlines is bad. Okay, so users take longer to click, they click less on the page. We make, therefore, less money because they click less everywhere, including the ads. We've run multiple multi-month experiments to see if people get used to this. We remove the underlines, did they just get used to this? And the answer is no. As far as we can tell, if we were to add underlines today, Bing and Google and other sites would be more effective for users. And discussions with Google folks tell us that they have observed the same thing, but the designers feel that the page is cleaner, right? And the underlines are so 1990s. And when you show people a side-by-side, people always select the page without the underlines. So Google, just historically, Google made the change in March. Yandex follows. Yahoo made this crazy decision to just underline ads because that causes people to click more on the ads so they make more money, but then they have this sort of inconsistent page with half underlines, half no. Unbelievable. And then we made the change this summer after a year of testing. We've improved some things. When you get close to the clickable click, we underline it quickly for you to help you zoom in, and that has helped us. But very, very interesting question. What should we do in this case? Is the industry standard so important? Does it take maybe a year for people to get used to this? Or are we just, the flash of the 1990s and early 2000s where every site had flash and then they're gone by now? Hard to tell. Okay, leaks. So shared resources are an amazing problem. This is a real practical problem in controlled experiments. Since we got people like Ruben in the room, I'll mention the term he uses a lot, which is SUTVA, the stable unit treatment assignment assumption, which means basically that when you run something against treatment, it cannot affect control, right? It should not affect control or else the result is invalid. So this is a necessary assumption. I'll share with you some examples where this happened. The first one, least recently used cache. So caches are used everywhere. Right? And so you have a cache on your machine and it tries to cache, let's say, the results for a query, right? Facebook is the #1 query on Bing and Google, believe it or not. Okay, so, we're not gonna recompute the damn thing, the 10 blue links or the 8 blue links for Facebook every time. We wanna cache those results. But then the problem is, for correctness, every experiment has to have its own ID as part of the cache key because if you fall into my experiment, you may get slightly different results even for a query like Facebook. So that causes fragmentation, but it also means that now the different experiments that are running are competing for this shared cache. So if treatment suddenly starts to use cache more or less, then it impacts control. If treatment is smaller than control, which is, by the way, we used to run experiments that had different sizes, like Why not run the treatment, which we're starting at just 5%, and the control is going to be the 95% or 1090. That doesn't work when you have caches, right? Because the 90% in control is just going to take up all the cache because it's least recently used, and then the treatment gets a small cache and it's slower, right? Things are less cache, it's slower, and it affects it. So very, very important. And then I'll mention a few more things here that in the notes. This is a really interesting side note. If you run multiple experiments like we do, anything that's higher level, like the page cache, tends to be useless because we run, just to give you this sort of interesting math, we run about what are called 15 number lines, concurrent number lines that users fall into typically. There's like 5 treatments in each. That means you have 30 billion fragmentation of the cache, right? All these combinations, so cache isn't useful at all. Another really great example is, the treatment uses the disk more, right? The disk is a shared resource. You're going to get screwed up. This one is an amazing one that happened to us. The treatment causes the server to crash, okay? And it takes control with it. Think of it like the potential outcomes, world that we do in causal reason. It's like you went into the parallel universe and shot the other person when you died. Right? So this is like amazing, right? You look at a scorecard where the server crashes whenever treatment runs, or rarely. It usually happens like there's some scenario in treatment, 5% of the time it crashes the server. The scorecard, the result that we generate to the users is this is a fine experiment, right? Because the control is just taken down with it. Pretty amazing. And then we don't know of really good solutions for this, right? We're thinking of, trying to deploy by even odd servers or data centers and all sorts of things that I think are not as nice as if we came up with a better solution. Okay, interesting segments. I'll just mention this in the couple of remaining minutes here. When you run an A/B test, can you provide interesting insights? So in a typical scorecard that we run, an experiment that we run, we give our users 1,000 to 4,000 metrics that could be impacted. Now, multiple hypothesis, many of those are going to show stat sig if you're at 0.05, but the point is, if there is something interesting to some component of the page, we want to highlight that. So you'll see sometimes that we have p-values of like e to the minus 30. Well, don't worry about multiple hypothesis testing, that thing is real. And that could be that some related search in some scenario is being impacted. But the question is, can we give our users highlight these things, especially when they're segmented? So a really cool result that we see once in a while is, if the user is running IE 8, right, a version of Internet Explorer, then this metric is going to tank. Very, very interesting. And because it's a small segment, and the overall result gets diluted. So can we come up with interesting ways? And we've built sort of decision trees. We have a mechanism to do that. And Susan Athies talked about how to do this theoretically, which is in practice a pretty hard problem to do. So applying machine learning to that, really, really interesting. Obviously, you have problems with multiple hypothesis testing. There's a few challenges I just want to close with. I haven't mentioned. I know they're out there. I have less experience in them, so I just want to not talk about things that we don't have. We don't have a sort of the classical social problems that Facebook have, and there's a lot of interesting problems there. Again, this is the violation of the SUTVA. Changes with user being logged in or not. In many sites, if you start the process, the user is logging in, their identifier changes. This is typically the identifier that's used to randomize. We're seeing some of those problems. I think it's going to be an issue for sites that are trying to optimize the users through the login process. We're playing with that a little bit. Again, I don't have a lot to tell. And then Yaju from LinkedIn, she used to work with our team at Microsoft, has some really, really interesting challenges at the last KDD conference. Okay, so I think calling the next speaker, and I'm assuming one question from the audience. Of course. I mean, this is not a hard thing to do, to say, okay, let's use a lower p-value. The problem with that are that many of the metrics that we really care about, like sessions per EU, we can't even move them at the 5% significantly, right? So there's a trade-off here. Some metrics that are short-term are very, very easy to move, and you get, very direct impact, and you can see 10 to the minus 6. But the metrics, the longer-term metrics, the one that we care about, session success rate and the sessions per user, we have several of these. They're very hard to move. So we actually need to reduce the variance on those. and we need to look, when it moves at lower values than 0.05, there's only 3 or 4, there's only 4 of them that we really use as what we call the shipping criteria. Thank you.
Next up is David.
All right, thank you. I want to talk about the games that can occur when we run experiments involving strategic agents. Want to recognize Panos Toulis back there. This is joint work with him. He's on the job market this year. And also this is also involving Ellery Pfeffer, who brought this problem to our attention, and also James Zoe. This is the classical story, of course, of experimentation. We have a drug, we have a control, we run a randomized experiment. If the treatment of the drug looks effective in the randomized experiment, then we approve the drug. Here's another story. Let's suppose that I'm deciding on a corporate car fleet. I have 2 cars. I bring the cars into my lab. And I'm going to estimate the effect of car 1 versus car 2 on emissions. And I'm going to choose the car for my corporate fleet with the best emissions properties. Seems like a reasonable thing to do. We know now that actually firms like Volkswagen were cheating in these experiments, in these tests. Okay. So what was going on here was that the test, the treatment, was a strategic agent. We were treating our world with a car provided by Volkswagen, but the behavior of the car was different when it was in the experiment than when it wasn't in the experiment. We wouldn't expect this to happen with drugs, but we see this does happen with strategic agents. Here's another example. This is the motivating problem that got us interested in this. It will not be surprising to those of you who work in ad tech to know that when you design your bake-off between 2 marketing firms, let's say they're viral marketing firms, the viral marketing firms will go out of their way to try to game the test that you've designed. So you design an experiment, you divide your customers into A and B in some hopefully randomized way. You give half of your customers to firm A, half to firm B. You look to measure the conversions of A and B over the next month, and you will give your business, say you're Amex, you will give your business to the firm with the highest performance in the test. So this is an experiment, and this is an experiment where you're trying to measure the quality of the firms as they would be if you picked them to run your business. But they may behave quite differently in the context of the test that's inducing a game. Right, so there's money in the mix, and maybe you choose the firm who's best at game theory, not the firm who's best at advertising. Right, so what's going on here is we have this cycle, or we have this chain. We have an experiment, we collect data, we do inference, we make a decision, and the treatments are economic agents, so there's this indirection where I treat some subset of my users with economic agent 1. Economic agent 1 now decides exactly what that treatment is. And the behavior in the experiment may not be the behavior later, and this may be a problem because it means that I don't do the correct inference about which is the best agent in this case. Okay, so I want to tell you a little bit about how we think about formalizing this. I want to tell you a little bit about some of the results we have. But the main thing I want to do is to encourage this agenda, which is thinking about strategic aspects of experiment design, so experiments as games. The way we formalize this is we have agents that are subscripted I, able to take actions, alpha I. So think about alpha I as the way you run your viral advertising campaign. This leads us to observe some data, and which you can think about as conversions on the users I've provided you with access to. We measure the sample mean on the users I provide you with, and the sample mean will depend on the action that you've taken. And you win the experiment. This is what you're trying to do as an agent if your sample mean is higher than the sample mean of the other agent. And so you're kind of interested in maximizing the probability that you win the experiment. So there are two types of strategic behaviors you might worry about here. One is a trade-off between risk and return. So I've got a little picture here. Here's the return, or the mean performance on the units in your sample, and here's the variance over the performance on the units in your sample. And suppose you have actions as agent 1 that kind of could follow this curve. So you could make a mean variance trade-off where you could choose to have lower mean but also lower variance. And if you're the stronger agent here, you're stronger because your mean is higher. You have an action with a higher mean than the other agent. You might choose to be a little less risky to improve the odds that you'll win the test. Whereas if you're the weaker agent here, you might choose to move to a riskier plan that will increase the odds that you will win the test. So we've got these kind of concerns about gaming here, where the agents are deviating from how they would behave if they weren't in this competitive setup. The other thing that often happens and will be interesting to us in modeling and solving this problem is that you can get interference where, let's see, how do I go back here? Where the action of agent 1 might also affect what's going on with agent 2. So I'll talk more about this, but in a marketing setting, you can imagine that the messages that you're using in your campaign are somehow interfering with the messages that the other advertiser is using in his or her campaign. All right, so just to give you a few numbers to begin to make this more concrete, suppose that agent 1 only has a fixed action, and the effect of that action is that the effect of agent 1's action is that a unit assigned to agent 1 will react according to a normal distribution with mean 9 and variance 1. So you can think about this as the model of the profit we receive when we take that action on a user sampled from the user population. And notice mean 9. Agent 2 here has a choice between an action with mean 1.5 or mean 2, but notice that the variance is higher for the 1.5 action. And notice that agent 2 is weaker. So actually, agent 2 in our experiment here can increase the probability it wins. This is the weaker agent by choosing a lower mean, higher return action. That's the type of gaming that we'd like to preclude. A little bit more on how we model this. So again, action alpha I. Let's define the quality of an action. This is what the designer cares about. So if you were to describe the estimand of interest, the designer cares about identifying the agent I who has the highest quality. The quality depends on the action of the agent. So the quality is the expected performance of a unit when agent I takes this action. And we can define this idea of a natural action. So the natural action is the action of an agent that maximizes the quality or maximizes the expected performance. And again, the objective of design is to try to identify the agent with the highest quality. What are we going to be doing when we're designing incentive-compatible experiments? We're going to be playing with a score function. We're going to be designing different ways, different statistics to compute on data to decide who is the winner of the experiment. So we'll denote that by phi, and it can generally depend on all of the observations. The observations of even all of the agents, not just agent I. And so now, once we've designed a game using this particular score function phi, then the probability that agent 1 wins is determined by the distribution on the transformed, on the score that we compute on the realized observations. And we can now define what it means to have an incentive-compatible experiment. Hopefully, you'll agree this is a natural definition. In words, what we're saying is that my experiment is incentive-compatible if the dominant strategy of an agent is to choose his or her natural action, whatever the choice of actions of the other agents. Okay, so it says you will behave in the experiment as you would behave outside of the experiment. So you maximize your probability of winning by playing as you would outside the experiment. So here's a good case. Suppose that the world is such that the outcomes are Poisson distributed, and that agents get to choose through their action the lambda parameter, so the mean and the variance of the Poisson distribution. We'll work with asymptotics here, so we'll talk about the central limit theorem, and we'll use that to give us a distribution on the difference between the sample mean and the mean implied by the choice of the agent. And once we use the central limit theorem, we can do some simple math looking at the difference between the normals implied by that. And the thing to notice here is that the probability of agent 1 winning as a function of the strategic choice of the agent, which is lambda 1, is monotonically increasing. So I've got lambda 1 in the numerator. I've got something that looks like the square root of lambda 1 in the denominator. If you don't believe me, you can simulate that out. What I'm showing you here is the probability that agent 1 wins. There are 3 different curves here reflecting different choices of agent 2. If agent 2 chooses lambda 2 equal 1, then the point is that the probability that agent 1 wins is monotonically increasing as agent 1 chooses a better action. The same for if agent 2 plays 2 or agent 2 plays 3. These curves are all monotone. Here's a bad case. So now suppose that the effect of the choice of the strategic agent is to parameterize a normal distribution. So you're picking the mean, you're also implicitly picking the variance. The variance is scaling very aggressively here according to the mean. So you can have a low mean, low risk action, or you can choose a high mean, high risk action. Do the same type of math. You now see intuitively in this equation something quite different. You see that the probability of winning may actually be decreasing in your choice of mean. I've got mu1 up here. I've got mu1. I've got the root of mu1 to the 4 in the denominator there. If you plot that out, indeed, what you find is that if I fix agent 2 to play a mean 2 action, then agent 1 actually can improve his probability of winning by playing a lower mean action. So this is a non-monotonicity. This is a gaming of the experiment. You can do better in this experiment by choosing a less risky, lower return action. Okay, so what can we do about this? One thing we can do about this is we can use variance stabilization transformations. So you can use the delta method, which is a technique from statistics that's quite widely used to reason about the effect of a transform on a random variable on a limiting distribution. You can use that method to try to find a transform f of the sample mean that will lead the convergence and distribution of the statistic to converge on a distribution with mean the transform of the original mean, and crucially, a constant variance. So by using these kinds of transforms, we can remove the risk-return trade-off. We can score agents based on an appropriate transform of the sample mean, and we can change the dynamics of the game. And if you look into the existing literature, if you have a family of models where the variance is proportional to the mean raised to the power beta for some beta that's strictly greater than 0, well, you can show that if you use this transform here, so if you raise the sample mean to 1 minus beta over 2, the transformed statistic has constant variance as you change the choice of the strategic agent in our world. So this seemed interesting to us. Let me show you what happens if we take this back to the example that I said was a bad example. The transform actually proposes that you shouldn't choose the agent with the highest sample mean. You should choose the agents with the highest negated reciprocal sample mean. So I'd like you to think about that. As you think about that, I'd like you to look just that we get this nice monotone curve now. Now what's happening? Actually, if the sample means were always positive or always negative, this transform is not changing the game. It would preserve the orders between the outcomes of the game. So if agent 1 wins before the transform, agent 1 wins after the transform. What's happening is it's doing something very subtle when one agent has a negative score and one agent has a positive score. And it's actually doing something that seems really bizarre. What it's doing is this agent, agent 2, with this high mean, high variance play, is going to be picked as the winner when its score is very negative. So it's like, if you do really badly, then I'm going to pick you as the winner because the way to think about it is it becomes possible that you're actually a very strong agent because you have this very high loci probability of having a very bad score. So it's like I'm grading tests, and if you're the bottom of the class, you may sometimes win. So it seems very paradoxical. And what it's doing, though, intuitively, is this stronger agent now is kind of happy with the high variance because it actually will be winning on the tail down here. We have more to say about this. I'm just about out of time, so I'm going to hold off on a few additional comments. Let me briefly point out that there's a family of transforms here. We don't need to use the transform here. We do, and we can. And make just a quick comment about interference and then wrap up. So we also have something to say about interference, which is that what we propose to do in the case of interference when there are multiple blocks, where the action of agent 1 might interfere with the effect of the action of agent 2, is if we understand the structure of the interference, we can back out the actions that the agents took by augmenting the data and adding additional blocks. So we can create additional experiments, and we can do inference about the actions the agents took. We can kind of reverse the effect of the interference and identify the actions, and then we push that through the original design. So in the paper, you'll see that we reduce the interference case into the no interference case. I'm going to stop, and maybe we have a time for a quick question. But thanks.
Questions or question? I had so many questions. If there isn't one, I'm going to ask one. Okay, so the lambda curves, the probability of choosing the action curves, that third one didn't seem monotone. Is that just my eyes flickering?
It was approximately monotone. There was probably a little bit of noise. Okay.
Okay.
It should be monotone.
I had more sort of substantive questions, which I think I'll keep for the panel.
Yep.
Thanks, David. Next up is Ben.
Where's the flicker? Okay, thank you. Can you make it larger? Shall I go now? So just couldn't make it bigger? Okay, so this is actually, John worked with a student and postdoc and colleague from political science and statistics, and also colleague from Rutgers University. So I hope you guys have seen enough data now on some theory. Give you escape. But we'll have a little bit data. So, oops, it's not. Oh, okay, thank you. It's a little hard. It's a technical challenge here. So I'll start with this example that there's a study called PAC-MAN. PAC is the pulmonary artery catheter which you insert, or doctor insert, into your heart to monitor the heart condition. And I cannot do it. Okay, thank you. So the question is, it's quite invasive. So the question is, does it help patient survival or not? And there was an observational study in 1996 and showed that there was adversary effect on patient survival, and it's more expensive. You can see that it's invasive, therefore you need more care. I guess I should have used the PowerPoint. Is that this message here? And then 2005, there was a randomized trial. So this one was done in UK with 65 intensity care units and about 500 in each arm. And the outcome is adjusted life years. One thing to point out that the control is not like no monitoring device. Was whatever the doctor thought was fit, but was not PAC. So you can see that it's not really PAC versus no. It's whatever they use. So you can see maybe a reason the result. And we also have a lot of demographic information, age, sex, and also some indicator like probability of death, basic wellness, and also like whether the patient was on mechanical ventilation when was admitted. And actually, I started working on this problem when I was consulting for eBay a little bit. And they were doing 8V testing. We're doing like adjustment using regression, also stratified groups. And then the question was, can we just keep feeding? And I said, definitely don't do that, because eventually you're going to fit perfectly. You're going to have the outcome as your predictor. And so the question is, if you do want to do selection, what would you do? How do you do it in a more principled way? Of course, variable selection now is basically under the name of Lasso, but it goes a lot earlier, right? In the 70s, in statistics, we have AIC, Akiyiki information, BIC, MDL. So I just want to bring people up that it's not just recently we consider models like, but they were now called L0, combinatorial kind of search, therefore it's not feasible. And Lasso really provided the convex alternative, and much research has been done recently. So it got a lot of attention, and you have good packages. But sometimes you still want to go back to these older methods. Let's just, if you will remember anything, remember this plot. So this is for the PAC-MAN data, and we're simulating the sense that we argumented the potential outcome by genetic matching. And then we simulated from this hypothetical population, we know both outcomes. And we made the P and N kind of about the same size. And you can see that the unadjusted is here. And this is the OIS. Because P equal to N, it makes things worse. So adjustment doesn't always help. But both Lasso, two versions of Lasso, made things much better in some sense than the unadjusted. And the difference between the two, if I would get to, is that this is a lot sparser. You get much fewer variables to look at. It's a pain. So this is a typical name and Ruby model. You assume the suitable assumption, and this is just the potential outcome. I'll just go for this group. And this is also typical. This is the observed outcome. Just more introduce my randomized mechanism is TI, not WI. And this is just the group sample averages and population potential averages. And the unadjusted, the simple sample difference. I already mentioned that you have many baseline in the pack data, but for IT type of search engine experimentation, you have the user's demographics. So you should have a lot of pre-experiment demographics you can use. And this is painful. When you do randomization, some disappears into the control group and some into the treatment group. So Friedman has been working on this and shown that if you only use TI and XI as the regression OIS adjustment, then if you have a balanced design, you're okay. Otherwise, you might get worse. And Lin, in a recent paper, showed that if you put the interaction, basically take both the indicator of the mechanism for randomization and XI, then you can remove that assumption. So that makes things nice, and then you can also, basically you end up writing two separate adjustments for control group and treatment group. And then you put them back together, you're basically imputing the adjusted treatment effect for the treatment group and doing the same for the control group. So for our problem, the Pac-Man, you have 59 covariates. If you want to like interactions, and later see interaction are important, you easily do two-way interaction, you get to like 1,000. So you now P is larger than N. And you can also do spline. You can just make things pretty high dimension by adding different interactions or polynomials. So that's what we decided to do, is just follow up on the Lin and understand, because the question come from eBay was, can you keep adding? And first, of course, you shouldn't. But in what conditions you can actually do that more cautiously? So we basically generalize the Lin approach and have the interactions for both control and the treatment and control. And you have two penalizations for the control, for the treatment group and the control group. But you don't penalize the main effect. Okay, of course, because you want that to be unbiased. And then it's equivalent to doing two separate Lasso problems, but also don't penalize the main effect. So it's just a little variation on Lasso. And that's our estimator. So you basically plug in the Lasso estimator now in the place where you had OIS, and you have the Lasso adjusted treatment effect estimation. And one thing I want to point out, this is for me from the thread, I did quite a bit of theoretical work on sparse modeling under the linear sparse model. There's this added benefit to move out of this assumed linear model. You basically assume all the covariates already in the right form, because you assume it's linear. And this, using the Neyman-Rubin model, basically, in some sense, is a misspecified model, allow you to consider the question which is very relevant in practice. Should you transform your covariates so that the linear effect will be more holding, right? So this separate the method from the model, I think needs to be done a lot more than assume the model and just do things under that. You'll hide a lot of problems and make the theory less irrelevant. We want to look at, even I kind of critiqued asymptotic normality yesterday, but still I think that's what we're doing here. And can you estimate asymptotic variance? But it's quite similar to the OIS. So this work builds up on Freeman's work and Lin's work, and there's a bunch of work recently on P larger than N, but in the causality framework, but basically assume high-dimensional linear regression models. So it's very different in that sense. We're kind of looking at the Neyman-Rubin model. I think there's advantage there. And so the key assumption beyond the OIS adjustment is actually really saying that the potential outcomes have some major pre-experiment variables in the right form. If you do decomposition, then you more or less have kind of like linear model, but these two are dependent. They are not independent, because this is just, the definition is the difference. So you involve both TI. Oh, this is on the population level. So you assume that there's this decomposition for the potential outcome which you don't observe. And later, I was talking about the residuals. Okay? You basically assume that the potential outcome has been decomposed in this way, and the conditions, that's what's telling. You have centralized false moment assumption, similar to Lin, but the added is that we need conditions on the error term, which Lin didn't. Because now we're imposing a sparse decomposition. And these are the further assumptions of the cone invertibility, which were true if you assume sparse linear model. Basically, all the research for the recent years, really, we figured out that we know that with duly squared, you need Hessian to be relatively, not degenerate. That's what we need too. But in high dimension, the Hessian in the P dimension is always degenerate. So what you need is, in the sparse low dimensions, the Hessian is not degenerate. That's basically what you need here too. And this is a scaling assumption. It's a little stronger for under the linear regression model, but it's what people need for debiasing right now. It's kind of frontier Lasso right now. So then you can prove the asymptotic normality, and you can show that it's better than unadjusted, and you also can do a conservative asymptotic variance estimation, just like Neyman did in his old paper for the unadjusted, for the Lin paper for residual sum and squares. So here's come question: how does this theory have anything to do with my Pac-Man data? Random try. I do believe that even you, sorry, I want to go back. Here, yeah, thank you. It's good to look at these conditions. So you look at the false moments, it's not too small, but luckily when you get this high, it's not the ones we selected. And you can look at the second moment, again, not too horrible. So this we want to be going to 0, it's not quite, but it's not 100 or million or something. Okay, so this shows that it helps you to make judgment call how my sparse decomposition holds. It's not perfect, nothing's perfect, but it's not horrible. So it's better to show even you can never prove with 100%. So that's what we got. So this is unadjusted, still kind of negative side, means the quality life year decrease, and the OIS and the Lasso, different two versions. So this is version I want you to bring your attention, especially for this community, is that this is the typical Lasso. You do Lasso, and then you do, I think we didn't do OIS adjustment. Here it's like, for any fixed lambda, you select a variable, and you do OIS right away. Do a bit bias correction, and then you cross-validate the two-stage estimator, okay? And that actually is better than doing just the selection. You correct a bit of bias, and it really adds to sparsity. So that's just a fine modification, but I think if you care about bias, this is a better. Actually, for this problem, it doesn't hurt too much, but in general, it's better. So the Pac-Man data result shows that it moved to be more negative, kind of in line with the observational study, but still not significant. And it doesn't show it's not there, just the data doesn't really can prove that. So accepting non-hypothesis doesn't mean prove the non-hypothesis. And the intervals for regression-based, including OIS, Lasso, and different versions, are shorter. But that's what I'm bringing attention to. This is not causal, anything, but it's very suggestive. It gives you a way. So this one really select very, very few dominant covariates for prediction. This is something you can look at in the future, right? For this, it's a few more. So this we didn't realize actually sparse adjustment really works quite well for this case. And if you look at the bias, they're all pretty unbiased. Even they both, in theory, biased. So what do you think about it? My adjustment I'll show you is really a contrast. You have this high-dimensional beta selected, but projecting a particular direction. So that's a much easier problem than estimating all the betas at every component scale, because adjustment is the main effect. And here, what dominates is the variance. They're all conservative, and we do reduce the length compared with unadjusted. But look at the model size. This is, you can see that really reduce with similar adjustment. Okay, so it makes it possible to look at. Otherwise, you look at all 59 of them, and it's hard to know. And we did also the selection stability comparison. So we just did subset selection and see which one is kind of stable. It's kind of towards a little possible suggested heterogeneous event estimation. We see that the top ones, this is selected by 0.4% of the time, or 40% of the time. So there are a few leading ones. That's what we end up selecting. Here is just a lot of correlation and make people, the covariates come in and out. So that's reassuring, like the ones we top is not completely over there, but the top ones. And then we compared about the two adjustments based on the Lasso, and they more or less the same. This one you can see that is a little bit corrected more because this is more biased, and the same way. You can see that this one tried to correct the bias, to give a bigger values. And then we can also see this adjustment as imputation, right? So we basically just imputing the potential outcome for the treatment group using the covariates. And that's what I'm saying that, so this is really a particular problem different from usually the Lasso problem. You're really looking at a particular linear contrast of the Lasso estimator. And that's an easier problem than looking at the whole vector. And that makes things better and less biased. And then we also compared with just look at, we know the combined effect, very little bias. And we now look at individually for A and B as imputation. Actually, they also have very bias because of contrast. First, we thought maybe there's some bias cancellation because you're making a difference. But what's going on here, actually, for itself, the bias is pretty small too. It's basically dominated by variance. And we also compare with Ridge. So this is on small data because this was run just a few days before I came. It's a small subset of data, so we can run more fast. Oh, sorry, I'd like to go back. Could I go back? I'm keeping right here. And Lasso actually, compared with Ridge, give very similar adjustment, okay, for this case. However, the interval Lasso, because for this problem, because their sparsity seemed to be that Lasso is a better fit for the problem, give shorter confidence interval. I think both methods, when you have a lot of weak adjustment covariates, Lasso might work better even, right? You have to find a fit to the problem. Both are, I think, are good methods. And here's the punchline. I won't show the last slide because I will stop here. So let me just write. I want to emphasize that this is just what people need when you assume the straight linear sparse model with edited Gaussian noise. Under the Neyman-Ruby model, you still need that. And the moment conditions, I think, are very telling. The moment condition, we need the false moment. We also need a second moment. So the practical approach, like recommendation from here is that you want to transform your covariates so you control the false moment, but at the same time, don't make the second moment too small. Because if second moment is too small, then you have no power to predict anything. If you go for the assumed linear regression model, then you will miss that. Because for you, it's already in the right form. And this moment condition is the same. Similarly, in the link case, it suggests that you want to control the false moment. And in a lot of the base covariant from the IT, a lot of the previous revenues are all long tail. So you should really do transformation. For our case, we did a little bit, doesn't really hurt, doesn't really help. We get like 5% improvement, we didn't report it, right? But for other long tail covariates, you should really try to do some transformation, square root, I mean the variance stabilization, what David was talking about, things like that to make things control the false moment. And if you look at the covariates picked up by the this method, which our recommended, it's basically age, and this probability of death is kind of wellness, and age is squared, it's not linear, and again, interaction between age and probability of death. And for the control, actually this shows, the control we know is a little thicker. The control patient just happen to be thicker after randomization. And it shows that this is the whether this patient needed mechanical ventilation or not when they were admitted, right? So this is kind of indication. So it's all the things we knew got picked up. And I want to just talk a bit, not showing the last slide because it's not quite right, last night revisions. It said, Susan talked about using random forest. And you can use also this other non-parametric method like this to be suggestive on the suggestive heterogeneous effect. I would think that we should talk about suggestive heterogeneous effect just so that we don't think people would prove causal effect, but they're useful. You can look at it, and if you really want to use the same data, have a better sense, you should split the data. Use part of the data to have suggestive and get suggestive causal effect using the other half of the data after you already fix the subgroup. Just get a little fine tuning of how we go for heterogeneous effect. Thank you.
All right, I would ask our three panelists to come up to the panel, and we can take a question for Ben while everyone's coming up. Yes?
Yeah.
So I'm kind of new to sort of all the econometrics, but from my memory.
I'm even newer.
Okay. So what I've learned is that there are sort of in traditional context of randomized experiments or internal context of sort of this. There's two sources of bias, right? There's the omitted variables bias, and then there's like the simultaneity bias, right? Lasso seems to be creating another source of bias, which is pushing the betas towards zero, right?
Yeah, yeah.
So when you run Lasso and then run OLS, you have now gotten rid of that pushing the beta to zero bias?
Not completely, but
not
help.
completely.
Help.
You try to help it, right?
Yeah.
But does it ever address the bias of what did I just say?
Simultaneity?
Not that one, the other one. What did I say? The
Omitted variables.
right? So actually Lasso is taking like all these vectors, right? So they have two covariates that are similar. Let's say they're perfectly collinear.
Yeah.
Lasso is going to pick one of them and get rid of the other one.
But remember, first, what we're using is really the predictive value. We're using adjustment. We're not using individual ones, so that's a lot more robust. Okay. And in particular, we're actually using a particular contrast, the beta projected in this linear form.
Okay.
So that's a lot more stable than selecting. But if you want to interpret, then that's a problem.
Okay.
Yeah. But for the adjustment itself, it's a lot more stable than the selection because you're doing the predicted value.
So my estimate of that beta, is not really interpretable. I can't use that for like saying this is the actual true effect, but it will help me predict better.
Yeah.
Is that
but for our case, we have 3 or 4, not completely stable, but relatively stable.
Okay.
Yeah.
Okay, thanks.
Awesome, so I'll open it up.
I wanted to ask about using the challenge of using A/B experiments to discover which segments certain conditions effective for, especially since it ties into other work on basically estimating treatment effects for different groups. So I was wondering, what's the sort of state of the art in the industry for using these A/B tests to discover, okay, this condition is working better for a certain subset, and then actually in real time trying to do some probabilistic personalization, where you're not saying, I'm done my experiment, I'm now delivering the segments. You're actually just using, okay, if this person's male, then 70% get condition A, 30% get B. If they're female, then those percentages are different. Just because it seems to tie in really nicely to really deepening the exploration-exploitation trade-off, where in a way you might never want to stop running experiments because you'll keep learning more about users. And so you might always want just 1% of people or something because that particular condition might work well for some combination of user features.
I don't know if I can talk about the state of the art in the industry. We, of course, test personalization algorithms. We test them as part of an A/B test to show if the new version of the personalization algorithm is better than the old one. I don't know if, Eitan, if you want to talk a little bit more, you do more of these Monte Carlo methods or multi-arm bandits. I mean, it's hard to say what the state of the art is without having the representatives from different companies here.
I guess maybe I'm asking because we've organized a workshop on NIPS on basically machine learning for automated experimentation and personalization. So maybe just more generally, what kind of approaches, even from a statistical perspective, might be being taken, where we're really trying to integrate discovering not just what works, but what's working which segment, and then actually putting that into practice?
Yeah, so we believe that it's better for us to get some insights about the performance of an idea that we have and iterate based on that. So we focus a lot on on a sort of pure A/B test, trying to analyze it by segments, by covariance, by things that you want to look at to understand if there are possibly some subset of the population that are doing differently and understand why. And one of the problems in A/B test that is well known is it tells you that A is better than B, but you never know really why, right? And it's kind of interesting that when an experiment wins, you'll see different people associate the win with different changes, especially if it was a big change. And so this is the one factor at a time change that we try to get teams to do more. When they have a big change, try to isolate what is really the cause of the win. Now, there are certain scenarios where it's sort of good to auto-optimize, but I think in the grand scheme, I would like to see teams develop some theories as to why the B version is winning, right? Because that leads you to the next set of hypotheses that can move you forward. You might get short-term more optimization by having something automated, but I think in the long run, the value of the insight, the human understanding of what is going on is highly beneficial.
Yeah, so follow up on that a little bit more, I would say that presently a lot of the use of heterogeneous treatment effect estimation for the reducement experiments is more focused around seeing if your experiment contains any metrics and to do sort of firefighting around like what kinds of subpopulations are negatively affected.
Right.
And it might also generate ideas for subpopulations that are possibly affected. And of course the bandits is like somewhere in between efforts to automate it. But I would say with the bandits we have some kind of a priori idea for what variables matter or
Yeah, I'll say that maybe to follow up on that, one of the most common things that we find is just bugs in the software, right? This is, unlike the theory, you're launching new code when you have new idea, and especially if it's like a UX change, it may not work on like a couple of browsers that, have small segments here. So the ability to say, this experiment doesn't look very good, but these two segments are really bad. If you get those two segments out, it's actually not a bad idea, right? This is the type of insight that is very, very interesting for us to find.
I think it's similar. When you do this global adjustment, right, you kind of can really mess up finding those segments. And then I want to make a point back to my talk is that the way we did adjustment, even you can use it as a surrogate, but it's not really the same thing, finding heterogeneous effect. That's a different metric. Right? People usually try to do one thing. In that sense, it's also suggestive. The metric is also not right. When you use the main effect adjustment as like an indicator, you probably should just deal with the heterogeneity. And even the non-parametric method indirectly also pull the data together to fit the model. Therefore, if one segment things just work very differently, you might miss that if you really want to concentrate on a segment. Or like personalized medicine, a subgroup of drug.
I would add that I think it's important to think specifically about what the intervention is that you are thinking about implementing. So in the case of social advertising, for instance, you might want to know the heterogeneous treatment effect of showing a social ad across different subpopulations, but you also might think about intervening by showing different sort of categories, different things. And those are two very different interventions that may not generate the same result. So I think Don mentioned this yesterday in the panel, that being specific about what the intervention is that you're thinking of is probably pretty important in that.
I would like to riff on this a little bit, and actually, I'd like to use the opportunity to ask Ronnie from his industrial perspective. We heard yesterday that there are salaries, there are annual bonuses that depend on code shipping. Are there
It's not code shipping, it's code making an impact.
Shipping and making an impact.
Yeah.
Are there games that are occurring within firms like Microsoft at the moment where developers are trying to do things to get either to get their things tested in the first place or to influence the results of the experiment in a way that would be ultimately not reflective of how the new algorithm would perform when deployed, maybe in combination with other changes. Is this something that you worry about? Are you doing things to try to address this?
Yeah, so this is sort of, are there cheaters? Is that, you know, the...
Well, cheaters, but...
Let me address this. I mean, what we're trying to do is sort of standardize on the way that we run experiments. So you have to run your experiment on a certain level, a certain percentage of the population, which, as I said before, is pretty large. Our biggest concern right now is just multiple hypothesis testing. You run your idea a lot, even if it's, you know, small tweaks of it, one of them may start to be significant just by chance. So we have a process that certifies results, and when you get something, you have to run it in a certification mode, which is very, very fixed, including running it and then reversing it, meaning you run it at, let's say, a 20% experiment, and then you ship it and keep a 20% holdout, right? So that sort of, you know, that replicability for us is one of the key things that allows us to gain confidence that this thing actually works in practice and is reliable. I'm less concerned with people intentionally doing it. I'm more concerned with the multiple hypothesis testing. They're just, somebody thinks an idea is good, they're going to try it a lot, and one of them will win by chance. And therefore, the certification and this ability to run it in what we call, you know, reverse experiment gives us some guarantee of higher belief in the data that this is a successful idea.
So the multiple testing, like false discovery rate, is not taking hold in this industry?
No, we use FDR in multiple scenarios on the scorecard itself or in tests that we do, but I'm talking more of just a person trying the idea a lot of times.
But you don't ask them to do that?
So we ask them to replicate,
Okay.
is the way we address that.
But you don't try to control like, how many times they...
No, we don't. Look, there's hundreds of flights that run on a given
Right.
day. Experiments, sorry, flight's an internal name. There's hundreds of these that run on a given day. So for me to try and somehow measure that somebody's running too many ideas, no, that doesn't
too
seem
much.
logical.
Yeah.
Yeah.
Susan?
Sure. So I had a couple comments and a question. So on just the state of the art and personalization, what's kind of interesting that, and I'd love to be corrected, but I've been talking a lot about this in the last year, and it's kind of interesting. I think the personalization algorithms themselves are like super complicated black boxes, I think, in the state of the art. There's a lot of different methods that people are using, and then they were sort of testing them just A versus B, which is kind of a funny dichotomy because like all this complexity and then just A versus B. And so I think it's sort of was a funny kind of gap in practice in the scientific literature that there wasn't that much on the heterogeneous treatment effects itself until recently. One thing Ben said at the end I want to emphasize, my methods, and I think, you know, other methods too do benefit if you're trying to actually do the subgroup analysis of the heterogeneous effects from searching for them on one population and then estimating them on another population. And so that's something I emphasize a lot in my work. And also what I find is it doesn't really matter if there's like real good effects. In like some sense, Lasso doesn't really emphasize that if you were just searching for interactions between your treatment and your covariates. If there's something real, then Lasso will find the right variables. If there's something real and sparse, Lasso will find it, trees will find it, everything will find it, and they won't find anything bad. But I've downloaded a bunch of field experiments from the web to test my methods, and the ones where there was like, the original experiment had a t-stat of 2 in the kind of aggregate effect, and then you looked for heterogeneous effects, and they weren't really there. If you kind of use the same data to search for the heterogeneity and then estimate it, you went horribly, horribly wrong. So basically, like when there's nothing there, that's when kind of what we call honesty of looking in one sample and estimating another sample gives you huge benefits. But if there is something there, you do sort of fine. Another comment actually is that, you know, Ben's methods of adjusting, it's very interesting that in a lot of industry, people have been, some of the engineers I've worked with have been really afraid to do any analysis on their experiment. They sort of feel like, you know, I've got A, I've got B, I should compare my means. If I do anything else, that's sort of bad. But then on some of these hard things like sessions per UU, Ronnie mentioned, and some of the stuff I've been doing on advertiser experimentation, we really barely have enough power to do what we want. And then these kinds of adjustments, especially like say adjusting for past history and making sure you have balanced samples, or if you have very skewed distributions, so you have some really big guys or really heavy users and light users and so on. If you do stratification or you do some of this adjustment, it can make a big difference. So I just want to sort of push that in some sense these techniques, like what Ben was suggesting, are more controversial than you might think. Because it sort of feels like I'm taking a clean experiment and then I'm analyzing it later and I must be fishing or breaking the rules. So I'm very happy that there's going to be more scientific papers that really show the benefit of that.
Yeah, the paper is on the archive. Hopefully was one part of the secular colloquium on causal inference at the Academy. So hopefully we'll get there through revision. So it's also at my website. But as we show that the first simulation, you can also make things worse. Right, so you have to be very careful. Yeah.
That's why people are afraid.
Yeah. So that's why you look for this evidence, try to see, I mean, theoretical conditions never hold in practice, but you try to find indications how horrible things can be. And eventually the money maybe will tell you whether it's good or bad, right?
Yeah, I want to ask the same question. And I think Ben and Ronnie would be best to answer this. If you're running more than 100 experiments a day, or 10x that, how do you do?
Sorry.
You got to get closer.
Oh, sorry. If you're running more than 100 experiments a day, how do you do knowledge dissemination? And specifically, if you're looking at getting more certainty around a hypothesis, how do you deal with replicating results? How do you disseminate that in an organization? How do you do knowledge sharing?
Yeah, so there's a few things that we do because we run so many concurrent experiments, and the problem is especially severe at Bing because we're essentially all optimizing the same page. When you're in a large site like MSN and people optimize different verticals, it's easy. At Bing, we have several methods. One is sort of prevention, which is that we have this notion of a number line where experiments are going to be disjoint. The number line is 100% of users, and the experiments that are going to run against the number line are disjoint. And teams figure out that these set of experiments have to be run, or they think in advance that these set of experiments have to be run disjointly, and so they get that feature. In addition, because there is a lot of concurrency, what we do is every night is we test for interactions in all pairs. This is where FDR comes into play. So think about a typical day, there's 300 experiments running, now you're doing 300 squared statistical tests. So we use FDR to try and prune that and make sure that we don't have a lot of false positives. I'll say that in practice, because of the prevention, because of the awareness that there could be interactions, there are very few times where we discover interactions on the live site. Real numbers that I'll share with you, maybe once or twice a week. The system will send out an email to the two groups saying, hey, we see an interaction between the two of you. Somebody will just manually put themselves into the two experiment and usually find the bug. So some people made assumptions that are wrong, and it's an implementation detail rather than a fundamental mistake, and then they'll either fix the bug or do the experiment serially. To me, the replication is the best thing, because I ran the experiment, I might have been in this 100 other experiments or 300 other experiments that were running concurrently. The fact that I'm running this 2 weeks later as the reverse flight, lots of other experiments are running. If this replicates, then it's probably robust against all these other changes going against the website.
So if there's no treatment effect at all, then interactions are highly unlikely, right? So since most of experiments don't actually affect your main metric, they cannot interact. So that's the question was more around if someone new joins the team.
Can you clarify? Clarify that? That I think there's a couple of reasons why that's probably not true. Did you just say that if there are no treatment effects, that there would be no heterogeneity in the treatment effects to be had, or?
If your experiment has no impact, like it literally does not change anything.
But what do you mean by impact? The average treatment effect, or the local average treatment effect?
Yes, the average treatment effect.
Okay.
So there, I guess it could still be
I think what you're saying is the distribution can still shift and the average stays the same.
You could have countervailing heterogeneous treatment
True.
effects and no average treatment effect pretty easily. Happens a lot, actually.
And a large sample that has probability 0.
What?
That is exactly 0.
To have
That's the faithfulness assumption for causal discovery. Yeah.
I mean, I'm coming from more the academic end, but when I was working with eBay, they also have this interaction between experiment problem, and maybe it's too idealistic. I would think that the company eventually, like especially service companies, we eventually have to understand the behavior of the customers, and that seems also in line with the long-term goal I have been hearing. Like, in short term, I will look at historical data when you know there might be interaction, feel some understanding into how things might have happened, and then with some hypothesis, same thing. Just so many possibilities. If you don't know what you're looking for, usually it's very hard to deal with after the fact. But if you go in with something that based on historical data, then you might find some interaction later you can take advantage of. And in theory, there can be so many different possible interactions, but if knowing the specifics of different experiments, understanding your customer base, then I think you might have a few low-hanging fruit of possible interaction which you can avoid, or really run experiment on different segmented markets so you avoid that interaction if you want to, or you model it, as Ronnie was saying.
Yeah, I mean, this goes back to the conversation yesterday about the difference between searching for things, finding things, and then folding that back into the theory, rather than using theory to guide whether what you're finding in a complex space makes sense or doesn't make sense. I don't think there was a clear answer to that. I think there was sort of a debate about it, and I think that's fine, which is that's the state at where we're at right now, I think.
Actually, the question I'd like to ask follows up directly on that. We've talked about machine learning in terms of the interpretation of results, and here's Microsoft running hundreds, perhaps in the future thousands of experiments, their principal agent kind of issues. When are we going to see machine learning recommending hypotheses for experiments? Do we see a shift from interpretation of data and interaction effects to automated hypothesis generation as we marry up big data analytics and seemingly synthesize and aggregate the hundreds and thousands of concurrent experiments going on? So
we do that in a setting that you might think of as too easy, but we do have groups that are doing sort of parameter sweeps over ideas, right? So, they'll say, here are 3 things that could be interesting. Let's do parameter sweep on all of them. So we're going to run a lot of experiments, changing the variables, maybe doing hill climbing or other things. That is already being done. It does have
Who's better, humans or the machines?
It's done by machines. So
what I mean is, whose hypotheses turn out to be better?
So at this point, we're not, again, you have to think of when you say hypothesis, is changing the parameter a new hypothesis, or is it a variant? I would say we're at the low end of the question.
By your criteria, who does better on the OEC front?
Depends on what machine learning or depend what person, right?
I would say that humans are by far better at
the best humans. If you take an average, right? That's the thing. You have a big variability too, right? I think the best.
There's no doubt that the breakthroughs that happen.
That's not a subtle distinction. The best humans still do fine.
Yes, that's my view.
But the average humans.
But with aided, I think AI, machine learning, you cannot just look at the data. And big data is really, there's no data, big data without heterogeneity, right? It's not IID going to infinity, right? That's not where we are. So you have to deal with the heterogeneity. And humans still very good with that.
Yeah, I'll say there's a paper that we wrote last year at KDD about sort of rules of thumb. And one of them was that when we do these optimization that, Michael's been talking about, of, sort of automation of parameter sweeps of things, we will get better results. They're going to be small. We'll get a 1 or 2% improvement to some key metrics. The real breakthroughs come from humans, if you want to say thinking out of the box, coming with some very, very different metaphor, making a change. We've had UX changes that were worth, over $100 million, right? And the only thing I can say is that there's no clear correlation between the effort that it takes to implement an idea and the result. And that, so you can have somebody working on something for 6 months and it will move nothing, or by a small percentage, and it could be something that somebody writes over the weekend that is worth $100 million. And that's sort of the cool thing about controlled experiments, because without them, it's the hippo that tells you what to do, right? And that guy over the weekend with an idea, there's one case I documented carefully because it was one of our breakthroughs. It was delayed from 2 releases, and the big release is like a 6-month release, because nobody thought it would work. And then somebody implemented over the weekend, and on Monday morning we had an alarm that we're making too much money and something is probably wrong.
How do you handle the case, Ronnie, where maybe you worry or other people worry that there's some short-term effect that So things look good in the short term. I want to kind of loop this back a little bit to incentives. It could be that incentives are misaligned and the engineers are trying to improve things that look good in the short term, looks good in your experiment. What do you do?
Challenge, one of the challenges that I pointed out, which is, are there novelty effects that would mean that some experiment is going to degrade over time?
Well, it's novelty. It could be equilibrium effects as well. It's not just novelty. Could be the
Well, almost by definition, I'm defining novelty as something that works in the short term and then dies over the long run. So we do look at the delta over time, and when we suspect that some idea may or may have this novelty effect or primacy effect, we will run it for longer. My sort of observation is that this rarely makes a big difference. So we may be overestimating the effect, but I've never seen something go from stat sig positive to stat sig negative, right? It may go less stat sig, maybe, that initially it was like 3% and it goes down to 2%. It doesn't really go down to 0 in most of the cases that we're looking at.
Do you think there's a difference?
I think there are such cases. They're very, very hard to detect, and this is why I put this up as one of the challenges. What are sort of early indicators that you may have a novelty effect?
And do you think there's a difference here between platforms like Bing, where I'm assuming you're looking more at the search results and the effect on your user searches than on the advertising side, but
both. I mean, we run experiments.
So I would hypothesize that you get these longer-term effects on the advertising side much more than you do on the kind of user-facing side, because you don't have this equilibrium dynamic playing through the environment that the system exists in as much. I assume you do on your user side, because you have some users who, over the period of 6 months, maybe a year, might decide not to go to Bing anymore, or start going to Bing. But
well, that's the sessions per user challenge.
So do you think about that?
We absolutely think about it. I mean, the people, as you say, especially in the ad space, where there are secondary effects happening in the ecosystem, are much more worried about these and the impact that they're making. And we, based on that background knowledge, we impose some constraints on what experimenters are allowed to do. I'll give you one example of a constraint that we use. For most experiments, if you are changing the space that you're taking for ads, then you must average the same vertical space, right? So if everybody knows if you make the ads bigger, there will be more clicks to the ads. So the challenge is, if you make the one ad bigger, let's say you had vertical links, which is an example that we shared, the ads become bigger, then you have to display fewer ads on average, so that if you average over all the pages displayed, the number of pixels that you took up is going to be the same in treatment as in control, right? So that's an example of something that we're very much concerned about. We know there's going to be a long-term impact if you start taking up more space. So we restrict the experiments so that on average they're about the same.
That's a nice
example. So that's how we handle it.
Yeah, that's good.
I have a question, actually starting with David for others and others. If you think of program trading in finance, now the discussion, if you think of computational advertising, a very similar discussion, because when you have targeting engines, that's the automated targeting, right? So then when anyone of us shows up at a website and an advertiser is bidding using a targeting engine, then you can get a reaction from other bidders. So you really have the equivalent of program trading. Everyone's bidding against each other, right? So have you folks encountered this much or thought much about it? So it's a bit of a continuation of, I think, what Dave was describing earlier, but in a much more dynamic way. And that sort of goes to this learning that we talked about earlier on. So at least I'm beginning to encounter this in my interactions with companies, and I was just curious whether you encountered any of this yourselves.
Well, there are some parallels here, of course. I mean, the HFT industry is of some concern, let's say, to people who worry about the efficiency of markets, and there's an active debate right now about how to redesign markets to essentially try to nullify the asymmetric advantage that you might have if you're a very rapid, low latency trader in that system. So people are talking about moving to a continuous batch auction, for example, so you put some millisecond delay in the market itself every time period. So I think there are analogies you can draw between, or analogs between, that design response and what happened in the ad auction space. So we know that early ad auction designs were using first price designs rather than second price designs. arguably the change was made because the kind of load and the strategic complexity of those earlier auction designs were a problem, not just on the servers, but on the wider ecosystem as well. So I think that there's that analogy, and there are design responses when we see strategic behaviors that we view as undesirable. I wouldn't want to draw a particularly tighter link, though, just because HFT is such an extreme ecosystem where if you read Flash Boys and other stories like that, you see the great extremes that those particular players in that industry have gone to try to game. I think our ad tech industry is a little behind there at this point, and maybe we hope that it will stay a little behind that extreme level of gaming.
I think we have time for one more question. So, Ravi?
Yeah, so actually, question for David. So I was trying to think of kind of the whole role of waiving informed consent, right? So even without strategic kind of angles, we worry about observer effects, right? So a lot of us, at least in academia, when you go out and try to run something in the field, spend a lot of time trying to convince IRB that we don't want to tell the subjects that they're in the experiment, right? And I'm sure Bing doesn't tell you that or Facebook doesn't tell you that you're part of the experiment. So I'm trying to get
that form with the 300 yes no doesn't work.
Exactly. so I'm trying to get a sense of is there something we're missing out? Like, are we safe when we sort of don't tell the people they're in the experiment, or there's still the possibility of strategic sort of actions out there, right? So that was kind of my question.
Is the question from the perspective of an academic viewpoint, or I'm not sure I'm following?
So I guess if I waive informed consent, do I have to worry about strategic actions? Does that problem exist?
On the part of the people in the experiment rather than an agent running the experiment.
That's right, yeah.
So I see. So you're thinking about some games that could happen when the gaming is on the part of the subjects of the experiment rather than, so in the work I was talking about, the economic agents were representing the treatment. I think you're talking more about the effect on the units or the users. If
right.
they know they're in an experiment or not in an experiment,
right.
will that change their behavior? Do you have a concrete example in mind here?
Well, most of the stuff we do, it's sort of, I mean, we make sure we sort of try to waive the informed consent out there, right? So I guess maybe I'm just trying to think about, is there sort of the element of, if enough people know that, like, let's say websites are experimenting on them, right? Then you could get into a situation where, then I think what you're saying might come into play, right? Like if everybody knows that in OkCupid there are multiple experiments running.
Let me give you one concrete version of this question. So suppose that advertisers know that search engines are learning how much they're willing to pay for different search queries,
right.
or are learning their conversion rates downstream, or are learning their click-through rates. And advertisers now aware of that might worry about the ratchet effect in economic theory, which is that it's hard for the platform to commit not to exploit that information over time. So if you're an advertiser now and you worry that Google eventually is going to know exactly everything about what drives your business, then you may worry about using some of the things that Google would like you to use, right? Are you going to reveal to Google which conversions matter to you and the value of those conversions, if over time you've basically given your business away to Google by now letting it learn exactly what's valuable to you and how much you should be willing to pay. I think that's an example where the awareness that advertisers are beginning to have about the way ad technology works is a problem, because it's hard for search platforms to commit themselves not to exploit that information. And this is one hypothesis for why we still see this ecosystem of ad tech around the big search engines, which would love to just take over and not have that other ecosystem. I don't know if that gets a little bit at this.
All right, that brings us to the conclusion of another awesome session. Let's thank the panelists.